Use the form of the definition of the integral given in Theorem 4 to evaluate the integral. So here's Theorem 4. And what this theorem was about was that, so this here is the definition of the definite integral. And I like this definition the best because it gives you the most intuition behind the method used to develop this. And it's, as you take the limit as n goes to infinity of the Riemann sum, this xi star is indicating that it doesn't matter what point you choose within each interval. As n goes to infinity, all of the sums, any Riemann sum you use is going to be the same. So you could do a left endpoint Riemann sum, a right endpoint, a midpoint, or some variation. As n goes to infinity, you get the exact same value regardless. Okay? Now, what the textbook mentioned was that in some cases, people like to give the definition of the definite integral using the right endpoint Riemann sum. And they do this because, like I just said, it doesn't matter. It doesn't matter if you choose the right, left, or whatever endpoint method. It's all the same. And so what people think is that, well, in that case, we'll present the definition using the right endpoint Riemann sum because the math is simpler that way, right? It's the way the endpoints are defined. It's easiest from a mathematical standpoint to use the right endpoint Riemann sum. Now, I like this definition because it reminds me of the whole way it was developed. But if we're going to, for the sake of practice, if we're going to do like a definite integral from like raw, from scratch, using the limit definition, then you might as well use the right endpoint method because, again, it doesn't matter which method you use. It's all going to be the same answer, and the right endpoint method is the easiest. And so that's what they're saying here. We're going to evaluate this definite integral here, raw from scratch, using the right endpoint method. And so what we want to do is we're going to, this is equal to, okay, this definite integral here is equal to the limit as n approaches infinity of the right endpoint Riemann sum as a function, we expressed as a function of just n. So what we need to do is we need to get r sub n and then take the limit of r sub n as n goes to infinity. Okay, so how do we get r sub n? Well, the way the Riemann sums were set up was that, okay, if we look here, the lower limit of integration is -2. The upper limit of integration is 0. Okay, and we've got f of x is equal to x squared plus x. Okay, now delta x is b minus a divided by n. B minus a, 0 minus -2, that's 2 divided by n. Okay, now the endpoints of the intervals are defined this way. I mean, this is general for if you're using any method, left, right, midpoint, whatever. These are how the endpoints are defined. X sub 0 is equal to a. X sub 1 is a plus delta x. So that would be -2 plus delta x. X sub 2 is a plus 2 times delta x. So it would be 4 divided by n. All the way to x sub n is equal to, that's going to be b. And you can see that that would be -2 plus n times delta x. So that's -2 plus 2, which is 0. B. Okay, so these are, this is universal for any type of Riemann sum you're doing. This is the notation. And the reason why the right endpoint method is preferable from a mathematical standpoint is that, so when you're plugging in the value of the x value for the interval into the function to get the height of the rectangle, with the right endpoint, it's easy. So for the first rectangle, you do f of x1. For the second rectangle, you do f of x2. Because these are the right endpoints. This is the right endpoint of the first rectangle. This is the right endpoint of the second rectangle. If you're doing the left endpoint or the midpoint, it's a little more complicated. It's not x sub 1. You're plugging in x sub I minus 1. Okay? So what we need though is, so R sub n is equal to the sum. It's going to go from I is equal to 1 to n. And the way these sums work is that, so I corresponds to the interval, the rectangle. Like I is equal to 1, you're at the first rectangle. I is equal to 2, you're at the second rectangle, all the way to the nth rectangle. So we're summing. So for each I, what do we want to do? We want to evaluate the function at the right endpoint, which is, in this case, is x sub I. So when we're at I is equal to 1, we want to plug x1 into the function to get the height. When we're at I is equal to 2, we want to plug x2 into the function to get the height. But then for each I, we also want to multiply that by delta x. Okay? So we're on our way here. What is xi though? So we need a formula, a general formula as a function of I to get any of these values. Well, that's easy. Xi is, so x1 was minus 2 plus delta x. x2 is minus 2 plus 2 times delta x. So xi is minus 2 plus I delta x. That's 2I divided by n. So this is the sum from I is equal to 1 to n, f of minus 2 plus 2I. There we go. So the next step is, here's our f of x. Let's evaluate f of minus 2 plus 2I divided by n. So what is f of minus 2 plus 2I divided by n? Well, we just evaluate it here. That's going to be, so this is x times x plus 1. So, okay, x is minus 2 plus 2I divided by n, and then x plus 1. Minus 2 plus 1 is minus 1, so minus 1 plus 2I divided by n. Okay, so let's distribute this. Minus 2 times minus 1 is 2, and then we've got, no, this would be minus 4I divided by n minus 2I divided by n plus, and then 4I squared divided by n squared. So 2 minus 6I divided by n plus 4I squared divided by n squared. Okay, now what is f of minus 2 plus 2I divided by n times delta x? So f of minus 2 plus 2I divided by n, delta x is, so delta x is 2 divided by n, 2 minus 6I divided by n plus 4I squared. Okay, so this is 4 divided by n minus 12I divided by n squared plus 8I squared divided by n cubed. Okay. All right, so there's f of xi times delta x. And so now putting this back into the R sub n formula. So we've got, here's f of xi times delta x. So 4 divided by n minus. Okay, so now this is the step where the summation properties comes into play. You need to use summation properties to solve this. So the first thing we can do is separate this into separate sums. So what we have is, okay, All right. Now what we can do is we can take out factors that aren't a function of I. So here we can do 4, we could take out the 4 divided by n. Here we can take out the 12 divided by n squared. And then here we can take out the 8 divided by n cubed. Okay, so now we can use the properties that the textbook gave us. We know the sum from I is equal to 1 to n of just I and I squared. So the sum from I is equal to 1 to n of just 1 is going to be n. Why is that? Because for each I, you're just putting 1. I is equal to 1, it's 1. I is equal to 2, it's 1. 1 plus 1 plus 1 plus 1, n times is just n. So 4 divided by n times n. Okay, what is the sum from I is equal to 1 to n of I? Okay, well, the textbook gives us that. It's n times n plus 1 divided by 2. Okay. What about the sum of I is equal to 1 to n of I squared? This is n times n plus 1 times 2n plus 1 over 6. Okay, so here's the R sub n. We've got 4. Okay, this is 6. Okay. So and we've got a 3 here. Okay, now let's create a common denominator. So we've got 12n squared over n squared minus 18n times n plus 1, or this would be 3n squared, over 3n squared plus, and then 4n plus 1, 2n plus 1 over 3n squared. So this here is 18n squared plus 18n. This here is 2n squared plus n plus 2n is 3n plus 1. So 8n squared plus 12n plus 4. So we've got 12n squared minus 18n squared minus 18n plus 8n squared plus 12n plus 4 all over 3n squared. Okay, 12n squared minus 18n squared is minus 6n squared, plus 8n squared is 2n squared, minus 18n plus 12n is minus 6n, and then plus 4, okay, all over 3n squared. Okay, so there you go. There's R sub n. And so this integral here is equal to the limit as n approaches infinity of R sub n, which is equal to the limit as n approaches infinity of 2n squared minus 6n plus 4 over 3n squared. This is a rational function, and we know that if you divide the numerator and the denominator by n squared, then you plug in n is equal to infinity, this limit is going to go to 2/3. So this is equal, this definite integral is equal to 2/3, right? It's going to go to the coefficients in front of the n squareds.